All right, welcome back to our lesson on how we can use the tangent ratio to measure the height of a tree. Now that we have our measurements, let's find out how tall that tree actually is. Okay, so here you can see a diagram of the situation, and if you recall from the previous video, I took two measurements, or my daughter and I took two measurements. One of them was the angle of elevation that the top of the tree made with the transit level, measured with the transit level, and that angle right here was 35 degrees. The other measurement that we took was the distance from the transit level to the tree, and that distance was 29.6 meters. Okay, so just two pieces of information. Now that might not seem like enough to determine the height of this tree, but with a few other assumptions, it is. The first assumption that we need to make in order to move any farther is we need to assume that this right here is a right angle. Basically that this tree is straight, right? It's going straight and it's perpendicular to the ground. We're also assuming, as we did in the last lesson, that the ground is flat. But there's another assumption that we need to make. We also need to make that assumption about the angle sums of right triangles being equal. And let's look at how that assumption shows up in our approach here. So in order to solve for the height of the palm tree, which I'm going to call x, I'm going to draw a triangle similar to the triangle you see here, right? This triangle has the horizontal line, the line of sight from the transit level to the top of the palm tree, and the palm tree. Of course, keep in mind that the transit level is a little bit above the ground, so we need to add in this 0.6 meters at the end. But we'll worry about that later. Okay, what I'm going to do is I'm going to draw a triangle similar to this triangle on my sheet of paper. So let's move this down, and let's see. I'm going to give myself a little space here. So I'll draw a triangle. First, I'll draw the base of the triangle. I'm going to draw the base as 10 centimeters long. Okay, so here we go. I got 10 centimeters. Now I want to draw a perpendicular to that 10 centimeter line. And I can use the dots on my dot grid paper to draw a perpendicular. Okay, so let's go ahead and line this up. Draw that perpendicular. Okay. Now I know that this length right here, the base, is 10 centimeters. And I know this is a right angle. So I'm getting close to having a triangle that's similar to, it's actually not similar to this triangle necessarily, but the triangle outside that existed outside when I took this measurement. But the next thing I need is I need this 35-degree angle. So in order to get that, I'm going to use my protractor. So I'll line up my protractor right here on the line. If you don't know how to use a protractor, there are videos and plenty of resources out there that you can use. You can watch other videos right here on YouTube on how to use a protractor. But I'm going to line up my protractor and I'm going to mark right here at 35 degrees. Then I can use my straight edge. And looks like I didn't draw my perpendicular quite high enough, so I'll have to extend it. All right. Okay, so let me extend that perpendicular. I'm running into my other triangle here, but that's okay. I've got enough space. Okay, so now I've used my protractor to make this 35-degree angle right here. This is where that other assumption comes into place. I know this right angle corresponds to this right angle right here. I know this 35-degree angle corresponds to this 35-degree angle right here. And by assuming that this triangle has the same angle sum as this triangle, I'm assuming that all right triangles have the same angle sum. Therefore, these two must have the same angle sum. So by assuming that this triangle has the same angle sum as this triangle, it follows that this angle up here must equal this angle up here, meaning that these two triangles are similar. All the corresponding angles are equal. Once I've set that up, I can now measure this triangle, and I can use my proportionality rule of similar triangles to find this length. So let's go ahead and do that. First of all, we're going to need to measure this length right here. And lining that up, I get that. Let me move it over a little bit so you can actually see it. Lining it up, I get that that is 7 centimeters. It looks pretty much exactly right on 7 centimeters. So I'm going to say this is 7 centimeters. Okay. So I've got 10 centimeters here, 7 centimeters here, and then I've got these two lengths right here. So now I can set up my ratios for the to use the proportionality rule of similar triangles. All right, so I'll do this one first. So I'll say, okay, this side here, 7, divided by this side here, 10, is equal to this side here, x, divided by this side here, 29.6. Okay, so now in order to find the value of x, I'll just cross multiply. So I get 10x is equal to, let's see, 7 times 29.6. I'm going to pull out my calculator for that. So 7 times, it's a little dark. Let me lighten it up just a little bit. 7 times 29.6. Okay, I get 207.2. So 207.2. And now I divide both sides by 10. And what do I get? Well, I get that x is equal to 20.7 if I round to the nearest tenth of a meter. So this length right here, x, is 20.7 meters. So what is the height of the palm tree? Well, now I just need to add in this 0.6 meters. And so the tree height, well, let's just add that. So 20.7 plus 0.6 is 21.3. And therefore, I can say the tree height is 21.3 meters. Okay, so I just found the height of the tree, and that's great. I'm excited about that, right? That was my goal. But though you may not realize it, there's actually something much more interesting and powerful right here on this piece of paper that we can use in many different situations, okay? Because we're assuming that all right triangles have the same angle sum, what that means is all right triangles with the 35-degree angle must be similar to this triangle on this sheet of paper. Any right triangle in the universe, if one of the angles is 35 degrees, that right triangle is similar to this right triangle, which means that this ratio of this side to this side, the side across from the 35-degree angle and the shorter side next to the 35-degree angle, in other words, the side that's not the longest side, and we don't know what that length is at this point, the ratio of these two sides will be the same in any right triangle in the universe with a 35-degree angle. So, and I know what that ratio is. I have it right here on my sheet of paper. It is 7 over 10. In other words, 0.7. Now this is a powerful tool. Like if I want to go out and do a bunch of measurements with triangles similar to this, I have a ratio I can use. And I don't have to keep remaking this triangle over and over. So you know what? Maybe I could just make a whole bunch of triangles like this with different angles, different right triangles with different angles, and I could find this ratio in all of them, and I can make a table, and I can use that table to do all kinds of measurement. What do you think? Should we do it? Yeah, let's start it. Let's see how far we get. Okay, so I've decided to call this ratio the tangent ratio. Actually, I didn't decide that, but it's what has been decided, and we'll get into that later. But let's just say I've decided to call this ratio the tangent ratio. The ratio of the length across from the angle to this length next to the angle that's not the longest length. Okay, so that's what I'm calling the tangent ratio. Okay, and so I know that for any right triangle with a 35-degree angle, that ratio of this side to this side must be 7/10 or 7/10. Okay, so I've got some good news for you. I've done a little work in calculating a bunch of these. So I know from the problem I just did that the tangent, the ratio of those two sides, the tangent of 35 degrees is 0.7. So I was like, all right, let's do some more. So I did a 10-degree triangle, and for all of these I did a 10-centimeter base, and then I measured this side right here. So this was 1.8 when that's 10 degrees. Divide by 10, I get that the tangent of 10 degrees is 0.18. Did the same thing with 20 degrees. I got the tangent of 20 degrees. It's 0.36. I did the same thing with 30 degrees. The tangent of 30 is 0.59 according to my calculations. And then I did it for 40 degrees and found out the tangent of 40 degrees, 0.84. And then I ran out of space. And it also took some time. So that's the bad news is this takes quite a while. And I'm only doing every 10 degrees. Like, what if I want to know the tangent of 13.5 degrees or something like that? It would take a while to actually go through all the work of finding all these tangent ratios. But since this is such a useful tool, this fact that, for any given right triangle, it's similar to all other right triangles with one of those same angles, as long as you're not talking about the 90-degree angle, right? So any right triangle in the universe with one 10-degree angle will be similar to this and will have this ratio right here. The fact that that's true, that seems like such a powerful tool that, don't you think at some point someone would have already done all these calculations? And it turns out, yes, indeed, they have. Okay, so as I was taking a walk with my wife and my daughter a few days ago, we were walking past a house that had one of those like little libraries, like give a book, take a book kind of little libraries. And occasionally we'll find a nice little children's book in those for my daughter. And we looked in this one, and I found this book, and I was super excited. I got to share this with you. Actually, I should be on the big screen right here, right? So anyway, yeah, so we opened up the little door to the library, and I found this book here. Let me hold it up. And this book is it focusing? Come on. Let's see if I can get this to focus. There we go. It's called A Second Course in Algebra. Well, basically, this is just an old algebra book. So why was I excited about this? Well, first of all, let's get the date in here. So this particular algebra book looks like it was published or written in 1944. Okay, so what that means is it was published before calculators were a thing. Like pocket calculators didn't show up till long after 1944, and scientific calculators definitely didn't show up till quite a bit later. And also computers, while they kind of existed in 1944, nobody had them, right? Except like the US government, because they were trying to figure out the problems around the hydrogen bomb or the nuclear bomb. So they were using computers for that kind of thing. But no normal citizens had computers at that point, really. And so all these types of these computational things, because people didn't have calculators, they would put tables at the backs of these books to help you with computations. For example, you can see this first one has like squares and cubes and square roots and cube roots, tables of logarithms, all those sorts of things. those were the sorts of things that they would put in the backs of these books, right? And in fact, it reminded me that when I was in high school, like 20 years ago or whatever it was, over 20 years ago, I guess, 25 years ago, even then I had a table in the back of my my Algebra 2 book with trig values. And let me just show this to you. I'm going to zoom this in a little bit. So let's zoom in on this and check out this table. Okay, so it says table of sines, cosines, and tangents. And let's just look at the tangent column, and we'll go down to, let's see, the 10-degree one, and see it says 0.1763. Well, I calculated 0.18, so not too bad, right? Let's look at 20 degrees. Where's 20 degrees? 20 degrees, the tangent says was this 0.3640. My tangent of 20 degrees was 0.36. Again, not so bad. And let's just skip down now to the tangent of 35 degrees, the one that I used to calculate the height of the tree. And we see right here, tangent, so it has the angle and the tangent. So go down the tangent column, and we see here that the tangent of 35 degrees is 0.7002. So really close to what I got, as the tangent of 35 is 0.7. So the point that I want you to see is, you can calculate these tangents by drawing triangles, measuring them, and using the fact that any right triangle with this angle is going to be similar to this right triangle right here. But you probably don't want to do that because it takes a bit of time. So you're probably instead going to look these numbers up. Okay, so let's go back and redo that tree problem and look up the tangent value from the table. Okay, so let's bring that back up here. Okay, so I know that the ratio in the triangle that I measured outside there is x over 29.6. That's the ratio from the triangle outside. So let's write that in here. So x over 29.6. Now that equals the tangent of 30 degrees, which according to my table, get that up here, 35 degrees, might be a little small for you to read, but it does say 0.7002. I think you don't need that many significant digits, sorry about that. So we're just going to go ahead and do 0.7. Typically 2 to 3 significant digits is enough for most of your problems in this class. So now I would need to multiply both sides by 29.6 to get x by itself. Well, that means x is equal to 0.7 times, sorry about that, 29.6. So now I plug this in my calculator and I get 0.7 times 29.6 equals, if I round to the nearest tenth of a meter, 20.7. So x equals 20.7 meters. Okay, so that's the value that I got by looking up the tangent in a table. And I can check, and sure enough, it's the same thing that I got when I used the similar triangle method. But guess what? There's another method. And in fact, neither of the methods that I've shown you so far, making a similar triangle or looking the value up in a trig table in an old math textbook, or you can find these tables online as well. Neither of those is the method that you're probably going to be using most of the time. Now, I happen to think that having a trig table nearby is actually helpful, and so you will find one linked in the homework document, and also I'll put one in the video description. But I do think it's helpful to actually have one of those around when you're doing trig, because it's important to remind yourself that these are just, numbers in a table of values that you can look up. However, typically you will actually just use a calculator to calculate these things. So let's do that last method really quickly here. So we did the table method. the similar triangle method, and now let's do the calculator method. So the calculator method. Okay, so now I'm going to set it up as follows. I'm going to take my same ratio, x over 29.6, and I'm going to say that it is equal to the tangent of 35 degrees. Now, we take the calculator and we might notice that we have these sine, cosine, look, tangent right there. It's right there on the calculator. And so you can find out what the tangent of 35 degrees is using the calculator. So I could just plug it in, say tangent of 35 degrees, and you see, sure enough, it's 0.70020 with a whole bunch of way more significant digits than you're going to need to use. But there it is. Okay, so I could rewrite it there, or I could do some algebra and do it this way. So I'll just multiply both sides by 29.6, and I'll get that x is equal to 29.6 times the tangent of 35 degrees. And I can plug it in my calculator just like that. So 29.6 times the tangent of 35 degrees, and I hit enter. Sure enough, I get that x is equal to 20.7 meters if I round to the nearest tenth of a meter. Couple things I want to mention before we wrap up. First of all, if you're doing these in a calculator, you need to make sure your calculator is in degree mode. This is something that shows up, my students end up getting confused about all the time. Okay, so go to mode, check to make sure you're in degree mode if you're putting degrees in. Radians is something typically you'll end up studying more in Algebra 2, pre-calculus, and definitely by the time you're in calculus, it's pretty much all radians. But in this class, we're going to be focusing on degrees. So keep your calculator in degree mode, okay? The other thing I want to say about the calculator is this. We're used to think of a calculator as like something that does all these calculations. But for the case, at least for now, for the case of the tangent and the next lesson, sine and cosine, I want you to think about the calculator as just something that has all these numbers stored inside it. Okay, just imagine all these numbers are stored inside this calculator. So when you type the right set of keys, like tangent of 35, it just looks up that number from the table stored inside and gives it to you. Because these are all, just numbers that have been calculated that you can put into a table. Okay, so that will be all for this particular lesson. If you notice on the calculator or in the table, in addition to the tangent, we saw there was the sine and the cosine, and so those are the topics for the next lesson. Thank you for watching, and we'll see you then. Bye-bye.